Okay, so we're still talking probability, okay? We're still talking probability. If you want to follow along with any of the notes and formulas, I think they start on page 707 in your textbook. But I'm going to just I'll put them all up here on the screen for you eventually too. But I'm just going to talk, all right? I'm just going to talk about probability a little bit with you, some more complicated probability. We've done some basic probability so far, okay? Like, here's a standard deck of cards, okay? If I said to go ahead and draw a card, and then I'd ask you, what's the probability that you draw an ace? 4 out of 52, because how many favorable outcomes are there? 4. How many total outcomes in a standard deck of cards? 52. So the probability of you drawing an ace is 4 out of 52, which you guys said reduces to 1/13. Perfect. Okay? So we've done kind of some basic probability. Now we're going to get into what's called compound probability. Okay? That's going to be with and or statements. Okay? So let's say here's a situation. Alright? You're going to draw a card. Okay? And you can make it a game or whatever, alright? But basically, you win if you can draw a 10 or a jack. You win if you draw a 10 or a jack. What is the probability of you winning? What is the probability that you draw a 10 or a jack? 8 out of 52. 8 out of 52. Anybody anything different? We like 8 over 52. Obviously, we would reduce that, but 8 over 52. Jake, can you explain why?
Because it's 4 out of 52 to get a 10, and then 4 out of 52 to get a jack.
And then you just added them together?
Yeah.
Does that make sense? Does anybody think of it differently?
That's
how you guys did it? Okay?
Sure.
Alright. Sounds pretty good. I like it. How many favorable outcomes would there be in the deck? 8. The 4 10s and the 4 jacks. So there's 8 favorable outcomes over the total number of outcomes, which is 52. Alright. Okay, good. What is the probability that you draw a heart or a spade?
23 out of 52.
26 out of 52, which would reduce to a half. Because how many hearts are there?
13.
13. How many spades are there?
13.
13. And using the same logic Jake did, we just add those two amounts together. 13 plus 13 is 26, so 26 out of 52. Okay? Alright. Good. So I've asked you a couple or statements. What's the probability you draw a 10 or a jack? What's the probability you draw a heart or a spade? And you notice in both instances we were adding, right? Okay? Also, both of those instances have been what are called mutually exclusive events. Mutually exclusive events. Drawing a 10 or a jack. Those are mutually exclusive. Drawing a heart or a spade. Those are mutually exclusive. Let me give you an example of something that is not mutually exclusive. Drawing a red card or an ace. A red card or an ace. Those are not mutually exclusive. What do you think it is that makes something mutually exclusive?
They don't overlap.
What do you mean more? They don't overlap.
Because it's ace of hearts and the ace and the hearts.
So there would be cards that would fall into both categories?
Yeah.
Okay, very good. If there are cards that can fall into both categories, those are called overlapping events. If there are no cards that fall into both categories, those are called mutually exclusive events. When I say draw a red card or an ace, those are overlapping because there would be 2 cards that would fall into the red category and also fall into the ace category. So those would be called overlapping events, or definitely not mutually exclusive. So mutually exclusive events cannot happen at the same time. Alright, and that's kind of where we start your notes a little bit today. Okay? This is still Learning Target 10.2. We're still working with probabilities. We're just getting into a little bit more complex probabilities. Mutually exclusive events. Your book, for some reason, also likes to call them disjoint events. Okay? I think in Algebra 1, their textbooks use mutually exclusive. Same publisher, they use the word disjoint a little bit more here. Okay? Same sort of idea. Disjoint meaning they're essentially kind of separated out a little bit. They events that cannot happen at the same time. Like Isaac said, Well, there's two red aces, so they kind of fall into the red category and they fall into the ace category. Okay, so those would be not mutually exclusive. But when you do have mutually exclusive events, if I said what's the probability of drawing a 10 or a jack, all you do is find the probability of drawing a 10 plus the probability of drawing a jack. Okay? So if you want to do the probability of A or B happening, all you got to do is find the probability of A and add it to the probability of B. Okay? That's when they are mutually exclusive. So what is the probability of drawing, what's the probability of drawing a face card or a 3? What's the probability of drawing a face card or a 3? Well, what's the probability to draw a face card? 12 over 52. Plus, what's the probability of drawing a 3? 4 over 52. So 12 over 52 plus 4 over 52? 16 over 52, and we would reduce. Okay, I'm not reducing now just for the purpose of speeding through some things here. Okay, but make sure you guys do reduce your final answers in the end. I would not reduce my answer right here. Okay, because if you reduce 12 over 52, you're going to get something that doesn't have the same denominator as this one potentially, and then you got to change the denominators in order to add them together anyway. So I would leave them as 52s to start, get your answer, and then reduce at the end. Okay? But again, this is for when things are mutually exclusive. So when things are mutually exclusive, meaning they can't happen at the same time, and you do an OR, all you do is you add the two probabilities together. Simple enough? Okay? Good. Overlapping events. No, thank you. All right, overlapping events are events that can occur at the same time, like the red cards and the aces, like you guys mentioned. Okay, there are red aces. The ace of hearts and the ace of diamonds would fall into both categories. Overlapping events are events that can occur at the same time. And I drew a little picture up there, a little Venn diagram, maybe to give you a little bit of an idea as to what that might look like, and maybe why they're called overlapping events. Okay, because those circles overlap one another. Okay? The situation here is, let's say I have the numbers 1 through 10 in a hat. Okay, so I got all these 10 pieces of paper, I put the numbers 1 through 10 on this piece of paper, and I got the numbers 1 through 10 here in the hat. Okay? And let's say we want to find the probability that you can draw an even number or a multiple of 3. All right, you want to draw an even number or a multiple of 3. Well, if you kind of look at this, okay, all of the even numbers would be 2, 4, 6, 8, 10. All of the multiples of 3 would be 3, 6, 9. 6 fell into both categories. 6 is both an even number and a multiple of 3. So this is an example of overlapping events because there is an outcome that falls into both categories. Okay? Now, it would not work to just add the two probabilities together separately in this case. Okay? Because what is the probability of you drawing an even number? 5 out of 10. Okay? What is the probability of you drawing a multiple of 3? 3 out of 10. If I take 5 out of 10 plus 3 out of 10, you get 8 out of 10. Is the probability of you drawing an even number or a multiple of 3 equal to 8 out of 10? No. How many numbers do you see up there? 7, right? 1, 2, 3, 4, 5, 6, 7. There's only 7. So the probability of you drawing an even number or a multiple of 3 is really only 7 out of 10. So why, by adding 5 out of 10 plus 3 out of 10, why does that give us the wrong answer?
Because you have 1 in each.
Yeah, you have 1 that fell into each one, so didn't you add that 6 twice in a sense?
Yeah.
Okay, so therefore, just adding the two separate probabilities together does not work here. Although we will still do the formula that same way, we will add them together, but then we got to subtract out the number you added twice. You got to subtract out what you added twice, or what was in that overlapping part. Okay, so for example, okay, now here's the formula, which you'll want this for sure down right here. Okay, when you have overlapping events and I ask you what's the probability of A or B happening, the probability of A or B will equal the probability of A plus the probability of B, but then minus the probability of A and B occurring at the same time. You got to subtract out that part that you added twice in a sense. And then you can kind of see the math that I did for the one that's on the previous page, the probability of drawing an even number or a multiple of 3. Probability even is 5 out of 10. Probability multiple of 3 is 3 out of 10. Minus the probability of drawing a number that's both an even number and a multiple of 3. Well, that was the number 6, so that's minus the 1 out of 10. And you get your answer, like you guys said, it was 7 out of 10. Do you guys have any questions over this? Do you have any questions over my notation that I'm using right here? Everything makes sense as to what you're writing down? Speak up if you have any questions so I can help you out. Good? So far so good? So an example of using this. What is the probability of you drawing a red card or an ace? What is the probability of you drawing a red card or an ace? Don't just blurt out the answer. Tell me how you would get to that answer using the formula. What's the probability of you drawing a red card or an ace? Jake, you want to give it a shot?
So for a red card, it's 1/2, so 26 out of 52, and then ace would be 4 out of 52, and then there's 2 red aces, and there's 2 black aces, so it's minus 2 out of 52.
Very good. Probability of drawing a red card, 26 over 52. Probability of drawing an ace, 4 over 52. Probability of drawing a red card that is an ace, 2 out of 52. So 26 plus 4 minus 2 would be 28 over 52. Yep, 28 over 52, and then you would reduce that. Okay? Questions on using this? This is for overlapping events. Okay? Why is this different than the mutually exclusive events? Why does this formula have to be slightly different than the mutually exclusive ones?
You have events that occur at the same time.
Yep, you got events that occur at the same time. You're adding the same number twice, so that's why we got to subtract that part out of there. Okay? But overall, for the most part, when you do the probability of something or something happening, all you got to do is add the probabilities together, and if you did add a part twice, make sure you subtract it out of there. Okay, for mutually exclusive, or for overlapping. You got to subtract for overlapping. Sorry. Okay. All right. Let's see. Next, complement of an event. I'm not going to worry about the time either. I think I got it fixed, so I can go over 15. Complement of an event. Okay. When you see this little bar above the A, the probability of A with a little bar above it, that's the notation that our book uses for the complement of an event. Okay? Complement is really the remaining probability, or the probability of not A happening. Okay? Let me give you an example. If I'm a 70% free throw shooter and I go to the line, okay, what's the probability that I make that free throw? 70%, right? Okay, 70%. Okay, because that's proven. I've shot millions of free throws, and for my life, I'm a 70% free throw shooter. Let's just say. Okay, the probability that I make that free throw is 70%. What's the probability I don't make that free throw? 30%. How'd you get that? 100 minus 70, right? Because you know the two probabilities themselves have to add up to how much? 100%, right? Because when you shoot a free throw, only 2 things can happen. You make it or you miss it. Okay? That's it. Okay? But every individual, all right, is going to have different probabilities of them making it or missing it. Okay? But if you want to know the probability of them making it, or versus the probability of them missing it, you know the two probabilities got to add up to 100. So in other words, the probability of something not happening is always just equal to 1 minus the probability of it actually happening. Okay? If there's a 20% chance of rain today, what's the probability, or what percent chance is there of not rain today? 80%. Okay, 1 minus 20% is 80%. Okay? Sometimes it's easier to find complements than it is the actual probability. It's faster. Okay? What is the probability of you rolling a dice and getting a number that is less than 6? 5 out of 6. Okay? You could either do one of two things. You could figure out how many numbers are less than 6. Could be 5 of them. Or you could just figure out how many numbers are 6 or more. There's only one of them. Okay? So the probability of you rolling a number less than 6, alright, is going to be 5 out of 6 because there's only one way to get something that's 6 or higher. So 1 minus 1/6 would be 5/6. Okay? Basically just know that the two probabilities have to add up to 1 and subtract 1 to get the other. That's complement of an event. Okay? And we'll do a really interesting story problem with this type of complement idea too.
What is the bar above the 8?
It just refers to the complement. It's read as a bar, okay? But it's when you see that, it's just referring to the complement of whatever A is. So let's say A was you making a free throw, then this would mean not making a free throw. You can maybe just think of it as the word not too. Okay? That makes sense? All right? Good? Then, okay, here's the game. All right, here's the game.
Ooh, games.
Yeah. All right. I'll give you a coin and a dice. Okay. You pay me $1 to play the game. Okay. You pay me $1 to play the game, and if you can get tails when you flip the coin, and get an even number when you roll the dice, okay, I'll give you your $1 back plus an extra $1. So I'll give you $2. Okay. But if you don't, if you don't, we're not actually going to gamble. Right? This is on video, guys. I mean, come on.
Once we stop it, we can.
Oh, we'll pause it.
Yeah.
Video editing. Yeah. Great joke. We'll just stop. Be like, hey, we're not.
All of a sudden, Mr. Alexander's getting a lot of extra nice things here. He must be doing something on the side. All right, running a little gambling.
I only got $73. How many?
You want to gamble that 73? I can sit here for a while. All right. So anyway, here's the game. You got to get tails and an even number, and you get $2 back. Okay. But if you don't get tails and an even number, I keep your $1. Okay. Do you think that would be a smart bet for you?
Yeah.
Yeah.
Okay. All right.
Let's do it.
Okay.
Well, come on. I want to do it. I want to do it.
So he's going for tails and an even number here. We're not actually gambling. Okay? He's going for tails and an even number.
Wait, but you touched it. Yeah, you touched it.
Well, then we'll make it land on the table.
Tails?
Tails?
See? It's because you didn't.
Even number. All right. Okay, go again. Well, you said you're going to win at least half the time. You lose. We're even now. Okay, go again. Well, we're back up $1.
Oh, Bo's gonna make some money off this.
Nope, we're back to even.
I told him I went half the time.
Now you're down $1. You're down $2.
Oh, come on, Bo.
This is
Down $3.
Oh my! Call 1-800-BETS off. It's getting bad in here.
There we go. Money back.
Tails.
There we go.
Oh,
I'm getting that
down
every
$2.
time.
Oh, dice.
Down $1.
Nice.
Alright.
Your mother would be rolling around right now.
Back down $3.
Roll the dice first, Bo.
Like a 42
Dice first?
Do it
Dice
sometimes.
first.
I get that every time.
Okay, good for that. There you go.
Nope, back down to $2.
Win it back, Bo. You're just gonna win the whole. You gotta keep that.
Nope, lose. Back down to $3.
You talking.
Oh, here we go.
Oh, no.
Down $4.
Yeah, we gotta win
All right.
twice here to get back even.
Down 20.
Okay, hold on. So he went about, I'd say, what'd you probably do that? Roughly 12, I'd say maybe played the game 10, 12 times there, I would bet. Okay? And he ended up down $4. Okay?
I'm gonna quarter off the deal.
Oh, yeah. Take that back. Yeah, he does have my quarter. What was the probability of him actually winning? 1/4, I'm hearing? He thought it was. You thought it was a half at first, which is a common thought.
It's half of a half. Yeah.
Right. It's half of a half. Okay? Because the probability of you getting tails is a half. So half of the time he should get tails, right?
Right.
But then, of that half of the times he gets tails, theoretically, only half of those times is he also going to get an even number, right? Okay? Can you see this at all up here? Okay? So here are your outcomes. Pay attention to this, guys. Okay? Here are your outcomes. You could get tails followed by an even number. Yay, you win. But you also could get tails followed by an odd number. Loser. Heads, even, lose. Heads, odd, lose. Okay? There are 4 possible outcomes if you're going for heads, tails, even, or odd when you do this game. Okay? Only one of them is a winner. So the probability of him winning is only 1/4. Okay? Why? Well, how many outcomes are there when you flip a coin? 2. How many outcomes are there when it comes to getting an even or an odd? 2, even or odd. 2 times 2 is 4, or if you want to do them separately, the probability of you getting tails is 1/2, the probability of you getting even is 1/2, 1/2 times 1/2 is 1/4. Okay? So, when we start doing multiple events, multiple things happening in a row, we actually have to multiply those probabilities together. Alright? This is what it essentially means, but a lot of times you will just see the word "and" in there, okay? If you want to find the probability of A happening and then B happening, okay? This doesn't mean both at the same time. This is a multiple event situation. The probability of A happening followed by B happening can always be done by taking the probability of A times the probability of B. Okay? The probability of you getting tails and then rolling an even number would be 1/2 times 1/2, or 1/4. Okay? So the probability of A happening and then B happening, you got to multiply those probabilities together. Okay? If I'm an 80% free throw shooter, if I'm an 80% free throw shooter, what is the probability that I make 2 free throws in a row?
40%. No.
Well, what's the probability I make the first one? 80%, 8 out of 10. What's the probability I make the next one? 8 out of 10. So what's the probability I make the 2 right in a row? 64 out of 100, right? 8 over 10 times 8 over 10 would be 64 over 100, or 64%. Okay? There's a 64% shot that I make 2 free throws in a row. What's the probability that I make 5 free throws in a row? 8 out of 10 times 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 8 out of 10, or in other words, 0.8 raised to the 5th power. About 33%. So even as an 80% free throw shooter, I only got about a 33% shot of making 5 in a row. Okay? Because they got to happen over and over and over again. Okay? Saw a very interesting, well, to me it was, okay, as both a basketball coach and a math person, okay, end of the Notre Dame-Kentucky game. Okay? Kentucky's got the ball, it's a tie ball game, about 30 seconds left, they're going to drop a play, they're going to shoot the last shot of the game. Okay? Well, they drove in, got fouled with about 5 seconds left, made the 2 free throws, won the ball game. Notre Dame got not a great look at the end. Okay?
Almost made it.
Okay? Yeah, but it didn't. Okay? Now, somebody ran Ken Pomeroy, who does all the numbers, it's kind of like the BCS a little bit in football, but anyway, ran the numbers and the probability on what maybe was the best thing for Notre Dame to do in that situation. Okay? And actually, as far as probabilities went, because they found the probability, if Notre Dame would have just fouled early, so they would have had the ball, all right, and had time to run a play and things like that, the probability of them, according to what they had, and the math behind it was pretty decent. Obviously, there's so many other factors, but the probability of them winning was a lot higher had they fouled early in that shot clock, let Kentucky either make their free throws or miss them, whatever, and then have the ball and have control of the game to win it at the end. Now, you don't do that because you're thinking it's a tie ball game, I don't want to give the other team points. But at the same time, you follow them at the very end, you don't even get a great chance to win the ball game. And he had probabilities written out, how it worked, why it worked, and it was very interesting. Makes you think about your end of game situations and what you should do. So obviously it depends on the type of foul shooter you follow, and there's a lot of variables. But anyway.
Is this guy related to Mitch Pomeroy?
No.
Totally paid.
So anyway, I found it really interesting. He tweeted that out, and it just makes you think. As a coach, you like to be in control at the end of the game anyway, instead of watching somebody right in the last shot against you. So. But anyway, you take probabilities and multiply them together. All right? So, that is for multiple events occurring. All right, that is really it for what I'm going to give you today. I got a little more to teach, but I want to let you work just a little bit for 10 minutes. Your assignment on this is that, algebra 1.
We'll take it.
They're working on probability right now too, but it's a lot easier.
I'll take that. We'll take it. For sure.
I'm sure.
We'll take it.
What types of probability are they using?
Similar stuff, but they're doing the end in orbit. Page 710, 3 through 39 odd, 42, 44, 47. You should be able to get a lot of this done for class on Wednesday. Okay, you got about 10 minutes right now. Some of you will get a good chunk of those problems done, especially if you pick up on it pretty fast. But I'd like all those to be done Wednesday. Come to class with questions over what you don't know. Both of these should be done when you leave class Wednesday. Okay? Both of these should be done before you leave class. I'm going to give you class time to work on it, okay? During our block day. All right? So for right now, please work on 7.